Our next speaker is Edwin Lyman. Dr. Lyman is Senior Scientist and Acting Director of the Nuclear Safety Project at the Union of Concerned Scientists. His PhD is in physics from Cornell University. He is an expert in nuclear proliferation and terrorism and the safety and security of nuclear power. And he regularly provides invited testimony to Congress and to the U.S. Nuclear Regulatory Commission. His latest book is Fukushima, the Story of a Nuclear Disaster. In 2018, the American Physical Society honored Dr. Lyman with its prestigious Leo Szilard Lectureship Award. Dr. Ed Lyman.
Thanks. So is this working now?
Yeah. I believe so.
Because I don't have an outside voice.
I'll get this up for you.
So actually, Professor King just teed up things very well, because I'm going to be driving home the non-proliferation and security arguments regarding my concern for the use of HEU in space reactors. So I've been, along with Alan, working for decades to discourage and hopefully eliminate the use of, can you hear me in the back? Yeah. Eliminate the use of highly enriched uranium for civil applications. Most of those pertain to terrestrial uses. And as we face a potential new space race, which might be driven by the availability of space reactors, or limited by the availability of space reactors, I think the space reactor community has to think about the norm that has been established and how they may violate it. So I think at this point, the space reactor community has to think about preserving this norm or potentially undermining all the progress that's been made. So just to recap, highly enriched uranium has security risks in its use, even though most experts believe that a subnational group does not have the technical capability for significant level of uranium enrichment without the support of the state. That means that already produced highly enriched uranium, which could be acquired by terrorists through theft or diversion in processing or transport, that is an available route, and so limiting the access to HEU of terrorists means limiting the availability of the material. And the best way to limit the availability of the material is not to have it, because no protection system is perfect. HEU can be used in an improvised nuclear device known as a gun-type device. The simplest one was outlined years ago by Luis Alvarez, who pointed out that if you had enough highly enriched uranium, you could get a significant yield just by dropping one piece of metal on top of another. You would need about 50 kilograms or more in order to have such a crude device, which is small in comparison to the use to the most civil uses of HEU in the world. Most research reactors and isotope production facilities have far less than that on hand. So it's large in comparison to most civil uses, but not all, as we'll see. And if you're talking about a nation state with a moderate technical capability, they could certainly build an implosion device with 25 kilograms, which is the International Atomic Energy Agency's significant quantity, but could probably do with much less, 12 kilograms or even less. So that sets the frame. And so over many decades, the US and the Soviet Union exported tens of tons of highly enriched uranium around the world to civil research programs, reactors, and started to play catch up in the 1970s when it became apparent what the proliferation risks of that kind of activity were. So the US began programs to work on converting civil research reactors to use low enriched uranium instead, and to take back the highly enriched uranium that they had dispersed all around the globe. including many areas of security concern. And that has been a largely successful effort. It's still ongoing, but there have been significant achievements. And one should recall that the research reactor operators and the medical isotope production facility operators all protested vigorously that this would inhibit their capabilities, the performance of their reactors, the economic competitiveness of their isotope production, and all those were unacceptable to them. But over time, this requirement drove innovation. So when we talk about programmatic constraints or even engineering constraints on programs, it's frustrating to me that LEU, the use of LEU, is not regarded from the beginning as a programmatic and even an engineering constraint. If it were incorporated into the system, we wouldn't be having these discussions, and it would drive innovation, and I think it is in the work of Professor King and others. So according to Assistant Secretary of State Ford, as of last year, about 100 HEU facilities have already been converted to LEU use or shut down. About 4.5 metric tons have been repatriated to the US and Russia, and now 33 countries and Taiwan are now HEU free. And here's a picture of the current status. Obviously, it's the US and Russia are the dominant possessors of this material. But what about space reactors? So kilopower reactors, which use, even the smallest ones, strategically significant quantities of 93% enriched HEU. So the moon surface reactor, which is 1 kilowatt electric, would be almost 30 kilograms of U-235. The 10 kilowatt Mars surface reactor would be over 40 kilograms of U-235. And it's hard to see how the US pushing development of a space program based on the use of these reactors would not undermine this norm of civil HEU use, starting a space race to the bottom in this case, where various countries and national or private transnational corporations will seek to use the best available material and will not compromise their own ability to compete by doing something other than what the leader is doing. And the leader here is the US. So it'll undermine that norm. It'll increase security costs and risks. And the defenders of the use of HEU point out, well, it's the US, it's NNSA, it's within the US infrastructure and complex. We know how to protect this material. That's true pretty much. But we're not talking about that. We're talking about what if we inspire other countries and international corporations to do as we do, we are going to lose control of that material and stimulate HEU demand to the extent that new production, and we'll see how much, could be necessary around the world. Now, no country except Russia is believed to be currently producing HEU. The other HEU producers stopped a couple of decades ago, and that did more or less cap the total world inventory, which has been decreasing. And we should not be looking for applications that could actually drive expansion of HEU production, not only in the nuclear weapon states, but also in non-nuclear weapon states. Another interesting thing, which has not really been discussed, is what are the international, or the extraterrestrial or space legal requirements or obligations for deployment of direct use nuclear material like HEU in outer space. And I'm talking about beyond orbit, which is where it was currently, or the sort of the limits of where that issue was previously considered, putting HEU into orbit. But what if we're talking about extraterrestrial, actually human settlements on Mars or on the moon? What are the legal obligations for safeguards? And there's very little scholarship on that, actually. And so the final issue is the, I know, it sounds like a joke, but if you look at the legal questions, it's not. So, and finally, what about opposition to space reactors? Well, I'll talk about that, but the non-proliferation community is generally not opposed to nuclear power, but many members of that community would be opposed to an expanded use of direct use nuclear weapons materials in civil applications. And so promoting or an HU infrastructure around the world for space reactors could lead to loss of support or even opposition from a number of these groups. So undermining the norm, just to drive it home, we heard about Elon Musk already, and there's Blue Origin, which is Jeff Bezos's pet project. If the US continues to assert, as it has, that HEU is really essential for space power reactors, that's going to set the standard for these other countries. Like I said, they are not going to voluntarily or unilaterally make decisions or compromise to reduce their ability to compete against the leader. What about security costs? Well, for DOE, 5 kilograms or more of HEU metal is a category 1 quantity requiring the highest physical protection. Or for an HEU and an alloy as the kilopower fuel, 20 kilograms or more, but therefore even the smaller cores are category 1. Where LEU, on the other hand, is DOE category 4, which has very few security constraints, maybe too few, but at least that's the current status. So the category 1 requirements, not just for the mission itself, but also the entire fuel cycle, the production of the material, the production of fuel, storage, transport, and eventually the mission itself, that will require significantly greater security than if LEU were used. Again, in the US context, if we're already subsidizing that through HEU or leveraging NNSA's security, the actual dollar value of that extra cost may not be decisive. But what about other countries that are inspired to get into the game? Who is going to be enforcing the same level of physical protection? The current international standards for physical protection are relatively low, even for HEU, and they're much lower than NNSA's domestic requirements. So who is going to be enforcing the necessary standards for both security and for non-proliferation? If an HEU mission if a launch fails, that at least 1 or 2 nuclear weapons worth of material would have to be recovered immediately. So you need additional response capabilities than you might for LEU. And also under the new presidential memorandum, anything other than an LEU-fueled space reactor would require presidential launch authorization, presumably because of that security concern. So that's an additional constraint now on US launches. So what about these private enterprises? So they don't have access to the government subsidies that NASA essentially does by leveraging NNSA. But does that really going to inhibit them? Well, there are countries that possess HEU that have the capabilities to produce it, that may be willing to sell it to anyone who's willing to buy it with a more permissive security constraints than, let's say, what would be available from the US. And that's something to think about. Let's take the United Arab Emirates, okay? They want to establish a colony on Mars, 600,000 people by 2117. All right, maybe it's a joke, but does anyone really doubt if UAE wanted to buy their own space program, that they couldn't do it? So what about the HEU demand for this? Well, the Mars mission, as we heard, would require about 5 kilopower reactors for a roughly 5-person cruise, so roughly 1 kilopower reactor per person over the reactor life of 12 years. So that's about 2 nuclear weapons worth per person. So this city of 600,000, assuming they need to be fueled by kilopower reactors, would require, once you reach a steady state, you would require about 28,000 metric tons of HEU produced for every 12, for a 12-year reactor. So that would require, just for fun, 700,000 metric tons of natural uranium per year to support that colony. 630 million separative work units of enrichment. That's more than 10 times the current world requirement. And so it's absurd, all right? That can't be done. So these HEU reactors are not going to be the basis for a sustainable colonies in space, period. And so people are going to have to do better, all right? Are we going to be talking about energy efficiency on Mars and how long that'll take, where they can reduce their power demand? But back home on Earth, the proliferation implications of that kind of fuel production, fuel cycle, would unfathomable. So it's a dream, it's a fantasy. As far as something that's sustainable, we're going to need other solutions anyway. So what about safeguards on Mars? Again, in the Outer Space Treaty, bans nuclear weapons in space. Also, all international terrestrial laws apply in outer space. So that might mean the NPT, but will the US have a nuclear weapon status in outer space, where I believe there are no national boundaries respected? It's not clear, but even if it were, again, we're talking about non-nuclear weapon states who want to establish colonies and have large amounts of HEUs. So who's going to be inspecting or enforcing IA safeguards on Mars? Are you going to have to make sure in every mission that you have an IA safeguard inspector along with the mission? That would be pretty ineffective. So just something to think about. And finally, this issue of non-proliferation. Let me just take our organization as an example, Union of Concerned Scientists. We're neutral on nuclear power, provided it meets the highest safety and security standards. So if you're thinking about a uranium-fueled space reactor that's launched beyond orbit to the Mars or to Mars or to the Moon, and it's not turned on until it's well beyond where it could actually cause problems on Earth, I think we probably wouldn't have a safety problem with that, because then it's a different risk benefit. The risk is to the crew, and they have a lot of other things to worry about. But if you're talking about, so from a safety perspective, we probably wouldn't have a problem. But we do have a problem for the reasons I've just explained of establishing an HEU space reactor infrastructure. And so this, we will oppose that. And I imagine that other groups in similar positions would feel the same way. So you may be stimulating opposition that's not necessary by promoting or continuing to promote the use of HEU. So I'll stop there. Thank you.
Thank you very much, Ed.